Let's take a look at the data we have, though, and let's compare it to FMEDA data. First thing I want to look at is the Dow plant study. Dow has published a set of failure rate data, and I will say that several Exeter engineers have traveled to Terneuzen, Netherlands to speak with the Dow people, understand how the data was gathered, what was included in the data and what was not. We developed a pretty good understanding, and I thank them again for their cooperation and assistance. Here's the Dow data. It's a gray circle. I'm going to drop that gray circle right on this bar along the bottom. Roughly speaking, 5e to the minus 7. That's the failure rate predicted for a pressure transmitter. Now let's take a look at some FMEDA results and drop the FMEDA results on the chart. That's not a bad match. And remember that Dow includes all types of pressure transmitters. Old designs, new designs, microcomputer-based, old analog transmitters, and some safety transmitters. And it kind of looks like I don't have the exact distribution of which kind of products are in the Dow study, but it appears to me like an average of all these different types comes in pretty close to the Dow number. Not a bad match. What about ARETA? We took the data from OLF 070, which comes from the PDS database, 3e to the minus 7. And if I divide that in half to account for site-specific data versus product-specific data, I will drop that on the chart. Now let's take a look at the dangerous failure rates, because the ARETA data only is not the total failure rate, only the dangerous. Let's drop those FMEDA results, the light green circles, onto the chart. Not a bad match. I think if we take an average again, you might discover that the FMEDA results are pretty close. I do not have a distribution of exactly what specific types of equipment are part of the ARETA database, but in general I was told that most of the equipment were installed many years ago, and it's probably the population is probably dominated by some of the older instrument types like the 1151. This isn't a bad match. 1.5, half of this number, compared to 1.2 e to the minus 7. That's a pretty close match. That tells me, if anything, the FMEDA results are pretty accurate to realistic end user field failure data, and the Exeter FMEDA data is well matched to ARETA divided by 2. We can compare mechanical parts as well as electronic. Here's some numbers for FMEDAs. We have for the poppet type solenoid valve and a spool type. FMEDA can distinguish between these two fundamentally different designs. If I compare the average of those two numbers, go ahead, get out your calculator. 1.59 plus 5.66, 7, a little over 7, half of 7 is 3.5. That's, oh my goodness, that's very close to the Dow study. We definitely spoke to the Dow engineers, and we were told that they include all types of solenoid valves, poppet, spool, all designs in this data. So it is a composite, and we could take an average, and gee, that tells me we're really, really close. Let's compare to ARETA. ARETA is 9 e to the minus 7. If I divide by 2, down here on the horizontal line, we get a 4.5. That's not bad. That's pretty close. ARETA's a little higher than Dow, 3.5 versus 4.5, but They're not that far apart considering the uncertainty of failure rate data and the statistical collection techniques. We've also put on some published data from some of the certifications from a German certification body, and we see numbers like 8.59 e to the minus 9, and in one case, oh my goodness, 4.53 e to the minus 10. That's kind of like 70. That's kind of like 3 orders of magnitude too low. That's not good. Even the manufacturer's warranty data, as optimistic as it is, isn't nearly as bad as minus 10. Anyway, we plot those results and we discover that the manufacturer's warranty-based data and the cycle test data are totally inappropriate for process industries and should never be used. Oh, I see a question coming in. I'll read the comment. Who am I to challenge a number published by a reputable German certification body? I can tell you who you are. You are the engineer responsible for safety verification of your plant or your customer's plant. You are the engineer responsible to make certain a design has enough risk reduction. It's your job to know and understand what are reasonable failure rates and what are not, and to reject numbers that are not reasonable for your application in the process industries. I think cycle test is just fine for machine safety, where a solenoid valve might be opening and closing every few seconds, but it's not fine for the process industries. You must look at every certificate, look at the data, try to determine the method used to generate that data, but most importantly, to compare that data with known reasonability limits. Let's check actuators. Here's the Dow actuator number, 2 e to the minus 7. I'll plot that 2 e to the minus 7 on the horizontal line below. We can also drop in the Nemours NE 130 number. They only publish a number for an entire final element. You remember 400. We'll put that down here on the bar. Let's take the ARETA number and divide by 2, and we'll put that, actually it's identical. These things kind of all pile on top of each other. And let's take a look at some FMEDAs. One of the FMEDA numbers is exactly in line with the Nemours, ARETA, and Dow. 4.29 versus 4, or 2. We have some numbers that are 6, 6.84, 6.29. If anything, it looks to me in this case as if the FMEDA numbers are a bit pessimistic. We would better dig into that a little deeper and make sure the FMEDA results aren't too negative. How about valves? I see another question coming in. Are operating conditions considered? Yes, to a certain extent. In the FMEDA results, we have a number of 7 different operational profiles, we call them, which list a whole series of environmental variables based on international standards, and the FMEDA component data is published as a function of the operational variable. So for any given parts, we certainly would have 7 different failure rates accounting for 7 different operational profiles. Thanks for asking the question. More questions are welcome. Never a problem with that. Now let's take a look at valve data. First, let's get this Dow number. Dow publishes a number for a valve body. It is interesting that Dow separates the actuator from the valve. They have 1.4 e to the minus 6. Let's drop that on the line here below. All right. Where's ARETA? It's 8 e to the minus 7. And if we take half of that, will publish a number that's 4 e to the minus 7. Well, that's a lot lower than the Dow number. I do not know why. One would have to dig into the specifics. Nemur has that final element number, which is, final element number, which is a valve and an actuator. And so they've got the 4 e to the minus 7, which is exactly half. Now, let's take a look at these ball valves. Closed to trip, tight shutoff, 4.83. That's pretty close. That's pretty close to the Burita divide by 2 in the Nemur. And there's another one where the tight shutoff requirements generated a 1.35 e to the minus 6, which is almost right on top of the Dow data. And I explained once before that the failure rate when tight shutoff requirements are present is much higher than when there is no tight shutoff. And FMEDAs can predict that difference. I think those numbers are pretty close. We don't know the exact application conditions. I don't know if any of the offshore valves require tight shutoff or not. The experts I talk with tell me no, a small amount of leakage is easily tolerated, especially when you have a double block and bleed. Anyway, not a bad comparison. However, a number published by a German certification body is way below, like at least an order of magnitude, and that could be dangerous if someone designs and depends on these numbers to verify a